So picking up with problem number 3 in particle and continuum mechanics practice final exam. Particle moves in 3 dimensions under the Lagrangian. L equals 1/2 mr dot squared minus v of r, where r equals absolute value of r. Show that rotational invariance implies angular momentum conservation. That's for part A. Part B, use Noether's theorem explicitly to derive the conserved quantity. And part C, if v of r equals k r to the n, determine for which n, if any, the system has a scale symmetry. So this is a conservation laws and Noether's theorem problem. So the Lagrangian is L equals 1/2 mr dot squared minus v of r, where r equals absolute value of r. And part A here, rotational invariance. That implies angular momentum conservation. So because the potential disappears, let me start again. Because the potential depends only on r equals absolute value of r, it is unchanged under the relations r goes to capital R, r. The kinetic energy 1/2 mr dot squared is also unchanged under rotations, since rotations preserve lengths, and therefore the Lagrangian is rotationally invariant. And the canonical momentum is P equals partial derivative of L with respect to r dot equals mr dot. The angular momentum is L equals cross product R and P equals mr cross r dot. And check directly here. Derivative of L with respect to T equals r dot cross P plus r cross P dot. And since P equals mr dot, the first term vanishes. R dot x mr dot equals 0, and P dot equals F equals negative delta V of R. And for a central potential, delta V of R equals dV dr r hat. So therefore, F equals negative dV dr r hat, which is parallel to R. So we get r cross F equals 0, and dl dt equals 0. Angular momentum thus is conserved. Okay. Now for part B, we want to use Noether's theorem to, explicitly to derive the conserved quantity. Okay, so here for this, Noether's theorem derivation for an infinitesimal rotation by vector parameter epsilon. Pardon that horribly drawn delta. Delta r equals epsilon cross r. The corresponding velocity variation is delta r dot equals epsilon cross r dot. The Noether conserved quantity is q equals p dot delta r. Substitute and q equals p dot, the cross product of epsilon and r. And using the scalar triple product, p dot, the cross product of epsilon and r, equals epsilon dotted with the cross product of r and p. So q equals epsilon dot L, and since epsilon is arbitrary, each component of L equals r cross p is conserved. So what's going to happen is Noether's is going to give us d dt, r cross p equals 0. Okay. And for part C, we want to discuss scale symmetry here. So scale symmetry for v of r equals k r to the n. Let v of r equals k r to the n, and consider a scaling transformation of the form r goes to lambda r, t goes to lambda to the a t, r dot goes to lambda to the 1 minus a r dot. And the kinetic part of the action scales as t dt is proportional to r dot squared dt, and it goes to this lambda, the 2, the 1 minus a, lambda a t dt, and that equals lambda to the 2 minus a t dt. The potential part scales as v dt. Here's proportional to r to the n dt. That goes to this lambda to the n, lambda to the a, v dt equals lambda to the n plus a, v dt. So for the two parts to scale the same way, 2 minus a equals n plus a, so 2 minus n is 2a. Isolating a is 1 minus n over 2. So under r goes to lambda r, t goes to lambda to the 1 minus n over 2 times t. And the equations of motion have a scaling covariance for any power law potential, where v equals kr to the n. However, the action itself scales by the common factor lambda to the 2 minus a equals 2 minus quantity 1 minus n over 2 equals 1 plus n over 2. So s goes to lambda to the 1 plus n over 2 s, and for the action to be strictly invariant, 1 plus n over 2 equals 0 is needed. So n equals negative 2. And there are two levels here. One, the equations have a scaling covariance for any power law, v equals k r to the n. And 2, however, the action has an exact Noether scale symmetry only for n equals negative 2. For n equals negative 2, the scaling is r goes to lambda r, t goes to lambda squared t. So the associated conserved dilation here is d equals r dot p minus 2t h, where h equals p squared over 2m plus v of r. Okay, so that's what we have here. Sorry if I missed anything. That's problem number 3. Thank you very much and have a great day.